Hello, everyone. Welcome to the sixth iteration of the Massively Open Online course in digital currencies for the University of Nicosia. This is session 2. We're going to be talking again about the Byzantine generals problem. And I'm your host, Andreas Antonopoulos. We have questions from the forums submitted for the duration of the week. And of course, we'll be taking live questions through the Hangouts question and answer system, which will be curated by George, and I'll be answering interactively as we go through. Actually, sorry, my mistake. This is session 3, basics of cryptocurrency, cryptography, and Bitcoin digital signatures and hash usage, and the history of mining. So let's see. First question is, as far as I can understand, a Bitcoin address derives from a private key that is used as a factor in an elliptic curve multiplication function. So according to ECDSA, the elliptic curve digital signature algorithm, and specifically the SECP 256K1 scheme, which is the elliptic curve, the same private key always produces the same public key address. Although I can imagine that the probability of two different users to randomly create the same private key is extremely small, that doesn't mean it can't happen. Following that, these two users will have the same receiving address and the private key to sign the transactions referencing this address. How does the Bitcoin protocol address this issue? This is a question from Christos. So Christos, the Bitcoin protocol does not address this issue. In fact, if you think about it, this is probably the world's worst lottery. From this perspective, think about it this way. You say, although I can imagine the probability is extremely small. Unfortunately, our imagination is very limited when it comes to numbers with 77 zeros after them. The probability of generating the same public key or the same private key when selecting randomly from a field of 256 bits is approximately 1 in 10 to the 77, 10 to the power of 77. That's 10 with 77 zeros after it. Just to give you a perspective of what that means, you could divide this number by 1 billion 8 times over. So it's 1 billion times 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 1 billion. And to put that into a bit of perspective, if you generated 1 billion keys per second, picked 1 billion private keys a second, and you had 1 billion people doing this, then your chances would be improved so that now it would only be a probability of 1 in 1 billion times 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 1 billion. You haven't really put a dent. So you've got 1 billion people doing 1 billion keys per second, and you haven't really affected the probability. And if two users generated the same private key, and one was able to gain the other person's money, you just have the world's most difficult lottery ever that only draws a winner once in the life of the universe, and that winner gets to steal one user's Bitcoin. So the Bitcoin protocol does not address this issue because it's not an issue. The probability is not just extremely small. The probability is what we would call scientifically astronomically small. And that means that the numbers involved only make sense if you compare them to astronomical scales. What is more likely? That you will find the same key, or that the sun will explode before you finish? And the answer is really simple. It's about 1 billion times more likely that the sun will explode into a supernova before you finish searching this key space, even if you had billions of people doing billions of keys per second. Big numbers. It's really fun to contemplate, but it's very difficult to use the human brain to understand numbers that have 77 zeros. There is nothing in human experience that even comes close to understanding it. Wim asks, I'm not sure I understand if and how work is distributed among pool members? Does each mining member try to find proof of work for one block of his own, or is processing distributed? So Vim, if there is a pool, a mining pool, then usually what happens, and there are some differences in the protocols, but usually what happens is each pool member is trying to find proof of work, is calculating proof of work for the same block. They're all working on the same block. The pool constructs a candidate block and then distributes it to pool members who use different nonces as their starting point, and then try to calculate proof of work for that block. Now, to go back to the analogy I've used before of throwing dice, and where the target is to come below a specific number, that's what they're all doing. And it doesn't matter if they're all throwing dice at the same time. Effectively, they all have the same probability. So if there's 10 people doing it, then the chances of one of them finding it is 10 times is exactly the same for each individual, but the chance of the pool finding it is 10 times higher. So all of that hashing power is accumulated across all of the participants in a mining pool. So on a similar question about mining, Iodasia asks, to determine the proof of work, the nonce is incremented by 1 and then hashed, expressed in a number. The hash should be lesser than a predetermined target value. What is the value? Who and what predetermines this value, and where does it come from? Is there an official technical name for this value? Is this predetermined target value the same as the hash target value for regulating block creation and adjusting the time of blocks to approximately 10 minutes? And why must the proof of work be below the predetermined target value? Let's tackle these very, very quickly. So yes, there is a technical name for this value. It's called the difficulty target. The difficulty target is the same as the hash target value, the predetermined target value, the difficulty target. It's the target. And it is used, indeed, to regulate block creation and adjusting the time so that it's approximately 10 minutes. The target really determines how difficult it is to do proof of work, and that is calculated based on how much hashing power has been allocated to the network based on the time that it took to do the previous 2 weeks of hashing. So really, this value is predetermined, but in an interesting way. It started at a fixed number on January 3rd, 2009, and that was simply written as a static number in the code. It was a very low level of difficulty, which made it easy for basically Satoshi Nakamoto's laptop to calculate blocks approximately every 10 minutes. Satoshi Nakamoto set that value based on the computing power of their laptop so that it would fix the time of blocks at 10 minutes. From that moment on, that value has changed through a very specific process, and that process is the recalculation of the difficulty target every 2 weeks by dividing how long it took over the last 2 weeks to create the blocks versus how long it should have taken if they were exactly 10 minutes apart, and then adjusting proportionately the difficulty target. So for example, let's take last 2 weeks, 2016 blocks. That should take 2016 times 10 minutes, or 20,160 minutes, to find all of the blocks in 2 weeks. It should be exactly 20,160 minutes cumulative from the first block to the 2016th block inclusive. Now, if it's above that number, if it actually took longer to calculate 2 weeks blocks, that means that they were taking longer than 10 minutes on average. And then if you simply divide how long it took, the ideal number it should take, 20,160, by how long it actually took, the number of minutes it actually took, let's say it was 21,160. And you calculate the difference in those two numbers, and you multiply the difficulty target by that proportion. So maybe you adjust it, and maybe that ratio is 0.9. So it's a 10% reduction in difficulty because it was too difficult, it was taking too long. The ratio of time it should have taken versus the time it took is 0.9. So we adjusted proportionally by that number. So now the difficulty target is 0.9 what it was before. And what that means is that it has now become 10% easier to, or actually that the other way around, it would be 1.1. So 10% easier to find a block. So the block time should speed up by about 10% and get back to approximately 10 minutes. So imagine this number was set by Satoshi Nakamoto when Bitcoin was released to approximately what it would take for a laptop of that age to do 10 minutes. And then over time, every 2 weeks, it's been adjusted. Up a bit, down a bit, up a bit, up a lot, up some more, down a bit, up some more, etc. As more people join, blocks become faster, and then the network makes everything more difficult to adjust the time back to 10 minutes. And so the difficulty target has simply been fluctuating from that starting point to where it is today. This calculation doesn't happen in any specific place. It happens everywhere, meaning that every 2016 blocks, everybody in the network says, OK, the next block, block 2017, will have a new difficulty target. We know that because 2016 blocks have passed. So how do we know what the difficulty is for 2017? Well, let's count how many minutes it took based on the block headers for the last 2016 blocks, divide that, the ideal number by that, and adjust the difficulty target proportionately. Every single one of the inputs to that equation is the same for everyone who's on the blockchain. They read the same numbers, they plug them into the same formula, they come up with the same answer, and that answer that everybody knows is what the difficulty target is for block 2017. And then 2 weeks later, they repeat the process. So the entire network recalculates the difficulty and then has an expectation of what the difficulty should be, is required to be for the next block. And then miners know that they have to reach that difficulty, otherwise their block will be invalid. Michael asks, is it possible to have a transaction that has many inputs and many outputs? For example, inputs from addresses 1, 2, 3, 4, 5, 6, 7, 8, and outputs to addresses A, B, C, D, E. Yes, Michael, that's a really keen insight. That's a really important aspect of Bitcoin that is often misunderstood. When you first look at Bitcoin, you mostly look at it from the perspective of a single user who is doing transactions from a wallet that is run by a human and run to do the same kind of thing that you would do with a bank account payment or PayPal payment or writing a check, as we still do here in the US. And in that case, you think about a transaction and you think of it as having 1 or 2 inputs and 1 or 2 outputs, maybe with some change. But a transaction is not limited in that way. There are some size limits that keep transactions from becoming too large. There are some limits on the number of signature operations that occur within a transaction. Again, these are mostly denial of service protections. But you could have a transaction that has hundreds of inputs and hundreds of outputs. And not just that, these inputs and outputs don't have to be for the same person or from the same person. You can have a transaction that includes inputs from hundreds of wallets, from hundreds of different people, machines, software agents, all joining together in a transaction, and then paying hundreds of different destinations. And as long as all of the inputs and all of the outputs add up correctly, that's a valid transaction. In fact, this exact technique is used in a number of protocols, such as CoinJoin, which is a system for protecting privacy by creating transactions with many participants so that you cannot easily see, just by inspecting the blockchain, who is paying who based on a transaction. So as an exercise for those of you watching this, use one of the blockchain explorers and try to see if you can find some interesting transactions that have lots and lots of inputs and lots of outputs. Pat asks, why does the public key need to be hashed to produce an address? Why not just use the public key to submit to the network? What purpose does having the additional abstraction of an address serve? On slide 25, you say allowing for greater flexibility. Could you elaborate? Yes. In fact, actually, you can use just the public key to submit to the network. That particular formulation is called pay-to-public key, which is different from pay-to-public key hash or Bitcoin address payments, which is one of the most common scripts on the network. But there's also other types of script, like pay-to-script hash, pay-to-witness script hash, and pay-to-witness public key hash. And we're seeing a few new ones being developed. The bottom line is this. The reason this abstraction of an address exists, really, there are two purposes. The first and really important one is allowing greater flexibility. If you had a Bitcoin system that only allowed you to pay a public key, then you really couldn't do much to extend the system and create other interesting abstractions. You would always be paying a public key. But within Bitcoin, addresses can represent many things. Public keys, multi-signature systems. They can represent complex scripts that have time controls, conditional statements, and things like that in them. And all of that is abstracted as an address in such a way that if you're paying someone or something or a script, you don't need to know exactly how that works. In fact, you don't know what the conditions behind an address are. You just have a single format, which is an address, which is an abstraction. And that could be a payment to an individual's wallet. It could be a payment to a multi-sig system. It could be a payment to a time lock. It could be a payment to a vault. It could be a payment to a very complex script with multiple conditions. So flexibility in terms of being able to extend the system to allow all kinds of different payments that are not public keys, and yet have a single abstraction that you can code into a wallet that we call an address, so that a wallet doesn't have to be upgraded in order to be paying these new types of abstractions. It just needs to know how to pay an address, and then that address behind it could have all kinds of different scripts. This is really important for allowing upgradability and flexibility within the network. The other reason, which is a bit more subtle, is that this actually creates a layer of privacy and security. So if, for example, we discover 10 years from now that there is a way to reverse the elliptic curve multiplication using massive computing power, or there's a faster mechanism for doing it, so that a determined adversary spending hundreds of billions of dollars in computing could reverse elliptic curve public keys. Well, they won't find any. And the reason they won't find any is because we don't record public keys in the Bitcoin blockchain until after they've been usually spent with a signature. So the only time a public key appears is after a transaction has been spent. And at that point, if you use the system correctly, which means you only use one address for one transaction, and then you use a different address, by the time you see the public key, it doesn't have any money behind it because you've already spent it. What you see in advance is an address, which is a hash of the public key. The hash algorithm is a completely different algorithm, much harder to reverse than any type of factorization that we know. And so this provides two layers of protection. You would have to be able to break both hashing and elliptic curve multiplication in order to go from an address to a public key and from a public key to a private key and steal someone's money. So it gives us future proofing against developments in encryption. One of the things to understand is that in cryptography, there are no perfect systems. Every system of cryptography has an expiration date, and you don't know in advance how long it's going to last. But we've seen many systems in cryptography over time. We either discover better algorithms that can produce factorization or reverse cryptographic algorithms, or we discover flaws, or the state of computing advances enough, or all of the above. So having the hash actually is a level of security. Mark asks, page 18 describes how the transaction is signed. It doesn't describe the purpose of hashing. Is it just to create a fixed size message to sign to make it independent of the individual transaction size? Or is there another reason? Yes, and yes. The purpose of hashing is to create a fixed size message to sign. So that is one of the reasons. It makes it independent of the individual transaction size. The signature is independent of the individual transaction size. But the other reason is also to introduce a layer of abstraction between how a transaction is parsed, how a transaction is structured, and how signatures work. And in fact, we've seen now a development that changes the way the hash is calculated by combining different elements of the transactions in a different way. Essentially, what you do is you pick and choose which parts of the transaction you're signing, and there are different forms of signatures. Some signatures only sign a single input. Perhaps you would use that in a transaction that has multiple participants, like a coin join. Some signatures sign one input and one corresponding output. And the most common form, of course, is a signature that signs all inputs and outputs. And deciding which type of signature we're going to use is up to the wallet. And based on which type of signature it is, then different types of the different parts of the transaction are combined to create the actual commitment hash, the hash that is signed, the fingerprint that is signed for that transaction. So effectively, you create this hash as a representation of the data you want to commit to with your signature that cannot be altered. Again, it's a reason to create flexibility. Pat asks, could you elaborate on how mining pools split up the work? Slide 44 says, miners in the pool contact the pool server and make a get work request to get a block to work on. Does a miner just work on one block for the entire time until they find a solution? Or are miners constantly calling get work to get the updated block as new transactions are coming in all the time? And if new transactions are included in updated blocks, are they constantly starting over? No, that's not how it works. The way it works is you had the first idea correct. A miner works on one block until either they find a solution and win, or somebody else finds a solution, and it's time to move on to a new block with a new set of transactions. Transactions are not updated while the block is being processed. The miners call get block. They get they call get work. They get a candidate block filled with transactions, and then they start working on it. Now, in most of the mining pool protocols, the connection with the pool remains open, creating a bidirectional channel, which means that the pool can trigger a message back to the miner and tell them that a block has been found, or that essentially new work is available and that they should stop working on the candidate block they have. And the reason they would stop working on the candidate block they have is because someone else has found the block, has found the proof of work, or has done the proof of work and found the solution. And therefore, the competition for this round is over. And the transactions that were waiting have now been confirmed. And therefore, a new set of transactions with a new candidate block has been constructed by the pool. Some of the pool systems use WebSockets, or they use TCP connections with a keep alive option or heartbeat. And that way, the mining pool can essentially interrupt the work of the miners to notify them that there is new work available. Until they get that, the miners will work on that one block. Mayank asks, 20 years from now, the economic reward for hashing will fall to less than 1 Bitcoin. Needless to say, transaction fees will then have to increase to keep people interested in hashing. For an average 2,000 transactions per block, the transaction fee will have to be raised as high as 0.006 Bitcoin to maintain today's reward value. Such a high transaction fee will make Bitcoin commerce cost prohibitive. Yes, correct. But that's not how it will work. You're talking about 20 years from now. What we've seen with Bitcoin so far over the past 7 years is the number of transactions per block has been increasing at a geometric pace, which means that we're almost doubling every year. At the moment, we've got an average of 1,000 transactions per block. So in fact, as capacity in the block increases with optimizations such as segregated witness, perhaps a block size increase, perhaps some other changes into how transactions are constructed, for example, Schnorr signatures and things like that, we're going to increase space in the block. And so maybe 2,000 transactions in 20 years is a very, very small number. In 20 years from now, with repeated doublings, we should be looking at 200,000, perhaps 2 million transactions per block. Perhaps if this is now used for Internet of Things, maybe 20 million transactions per block. And so at that point, the transaction fees, the total amount of transaction fees will be high, but not because each transaction is expensive, but because there are many, many, many transactions. And that's always been the design concept behind Bitcoin, is that as the reward for new coins drops, the number of transactions increases. And 20 years from now, if we're doing 2,000 transactions per block, we don't need to worry about Bitcoin being so expensive it's failed. It's already failed. If Bitcoin is still doing 2,000 transactions per block, and those transactions aren't aggregate transactions for a layer network or something else, then Bitcoin isn't really growing. We would expect to see a lot more transactions. On a follow-up question to that, Ayudeji asks, how many transactions can make up a single block? Well, today's blocks have a 1 megabyte upper limit in size. And that means that with an average transaction of about 350 bytes, plus the overheads, you're looking at between 1,000 and 1,500 transactions on average per block. Nana asks, how come the first Bitcoin transaction was performed on block 170 and not block 1? Well, presumably Satoshi Nakamoto turned on mining and then went to have a sandwich and possibly went to bed and then got up the next day and said, hey, it's still working. Great. You got to realize that this is very early days. And block 170 is not that far in the future. Block 170 is what is it? A day and 5 hours, so like 26 hours into it. 144 blocks per day. So 170 blocks in is like 26 hours after the first block was mined. And perhaps the reasoning was, let's just let it mine without any transactions, see how it works. But a lot of tests had been run before then. And so No idea why that was the block when the transaction was done. But it proves another point, which is you can have empty blocks. You can have blocks without transactions. The Bitcoin system works quite happily with empty blocks. Moina asks, on page 38, it states that a new block is added to the local blockchain. Please confirm what a local blockchain is. I thought it was one unified chain. Is that not the case? So Moina, you have to understand that there is one unified chain over the long term across the entire network, because everybody has a local copy, and that local copy over a number of blocks, usually over 2 or 3 blocks at most, is the same as everybody else's local copy. So everybody's keeping a local copy, and these local copies are synchronized using the peer-to-peer network. Differences between them are resolved by calculating the winning chain through estimating the largest cumulative difficulty or the largest amount of proof of work in the longest chain. And that allows every local copy of the blockchain to be identical. Not for the last block, maybe, not for the last 2 blocks, because there might be some differences called forks, some synchronization delays. But within a couple of blocks, every local copy is the same. And so it is a unified chain. And the magic of Bitcoin is, how do you synchronize all of these local copies without putting anyone in charge through the process of the proof of work consensus algorithm? Nana also asks, Bitcoin history seems to be awash with many negative incidents, including a bug requiring a fork, and exchanges being hacked, and millions of dollars vanishing. Hackers stole $72 million recently from exchange Bitfinex, and there's many other examples of that. Yes. Are Bitcoin safe, and are any lessons learned, or more of these incidents keep occurring? Yes, yes, and yes. Bitcoins are safe. Lessons, I hope, are being learned. And yes, more of these incidents will occur. Why are these incidents occurring? The thefts that you see, first of all, in terms of bugs, bugs in the Bitcoin core software are now, like, bugs that affect actual funds are exceedingly rare. I don't think last time we saw a bug causing a problem in the network was 2013. And that was a temporary problem, was resolved within a few hours, and no funds were lost. The time where funds were affected, again, temporarily, no funds were permanently lost. The previous time was 2011. Nothing's happened since. The Bitcoin system itself is actually remarkably robust, considering that it runs 24 hours a day, 7 days a week, and systematically attacked. It is extremely safe. It's safer than any banking system that exists today, any payment system that exists today. However, this is the difference between the system as a whole, which is extremely secure, and individual wallets. And individual wallets can be hacked because individual wallets are controlled by who has control of the private keys. And securing private keys is not easy. Now, for individuals who use Bitcoin in a sensible manner, use security devices such as hardware wallets, or practice good information security, and granted, that's not very easy yet for most users. It takes quite a bit of sophistication. That makes Bitcoin a very safe mechanism. And so I'm comfortable holding Bitcoin and have not had my Bitcoin stolen. And a lot of users feel very safe in their control over Bitcoin. However, here's what happens. If you give control of your Bitcoin to someone else, which in Bitcoin for the first time in human history is not required. You don't need to give control to someone else. You can hold and control your own money. If you give control to someone else and they take control from many, many different people and they collect all of the money under a single system with a single set of keys that they control, and they get hacked, they lose all of that money. So the problem is that you have 72, in the recent example, $72 million in customer Bitcoins that are not being held by customers, that are being held by a single exchange with single control over those keys. If those $72 million dollars were held in 7 million wallets, then you would have to hack 7 million times 7 million wallets and 7 million different computers for 7 million people to get this amount of money. But if you give all of that money to one company and they control it, then it can get hacked. Bitcoin is a system where you control your money. And here is the lesson that should be learned. Your keys, your money. Not your keys, not your money. If you control the keys, it is your Bitcoin. If you do not control the keys, if you have given control to someone else voluntarily, it is not your money. You have given it on loan to an exchange. If the wallet is controlled by someone else, it is not your money. And when it gets taken from them, then the mistake was giving it to someone else in the first place. I used Bitfinex 4 days before the hack, in fact, to exchange some Bitcoin. And what I did is what I always do. I use exchanges to exchange. I don't use them as parking spots to put my money and leave it there, because I do not trust other people with control of my keys. I moved some money in, some Bitcoin. I converted that Bitcoin to another currency, and I moved that currency out. In total, my money was sitting on that exchange for about 20 minutes. And during that 20 minutes, I was taking a small risk. But before I started, I had zero balance on the exchange. 20 minutes later, I had zero balance on the exchange. And as a result, I wasn't affected. I've used several of the exchanges that have been hacked in the past. And I have not lost money at an exchange. Not with MTGOX, not with many of the other hacks. And so the reason for that is because I follow the lesson that I've learned, and I try to repeat to other people. If it's your keys, it's your coin. If it's not your keys, it's not your coins. Let's see. I think we've got a question from the audience. Hi, Andreas. Could you tell us your opinion about the possible malleability of transactions problem? Yes, transaction malleability is a problem in Bitcoin. It's been a known design problem since the beginning, which is that third parties can make subtle changes to transactions to create alternate versions of the transactions that have a different transaction ID. They can't change who gets paid. They can't change where the money is coming from. They can't change how much is being paid. They can't change the signature. They can't affect any of the monetary aspects of the transaction, but they can change its ID just in a very subtle way. Now, the bad news is this has been a problem. The good news is this problem is about to be fixed. One of the technologies being introduced this summer is called segregated witness. Segregated witness is an architectural change in the structure of transactions that moves certain data to a different part of the transaction and uses a different mechanism to calculate the transaction ID. Segregated witness solves third-party malleability completely. And once it's implemented, which is likely to happen probably, I would say, over the next 3 months, and once it is active on the network, people will be able to start using that feature. And as more people use it, the transaction malleability gradually goes away. Applications will be able to choose to use segregated witness. and they will be immune to transaction malleability. Shrikant asks, I read a newspaper article a few days ago about a blockchain editing system that has been developed by a professor at the Stevens Institute of Technology, has filed for patent with Accenture. Is it really possible to edit the blockchain? And if so, how could this be done? If this news is legitimate, how can this impact Bitcoin and other altcoins? So let's explain what happened here. The professor who filed this patent has created a new form of blockchain, which allows someone with the right credentials to go and change the blockchain. So they've basically created a blockchain that is not immutable, but a blockchain that is editable. They've removed immutability from the system. And the reasoning behind this is that this is something that banks and governments might want to do. I am extremely skeptical that there's any value in this. Making a blockchain, designing a blockchain that is editable, to me is a contradiction in terms. We already have systems of payments that are editable, and if you make it editable, it's not really a blockchain anymore. It's a spreadsheet. How can this impact Bitcoin? It doesn't impact Bitcoin at all. It doesn't impact altcoins. You can't change those. Those are immutable. It doesn't suddenly make them editable. It just means there are new blockchains that might be created that are editable, that will try to compete against Bitcoin by being different. In my opinion, by being less useful. Immutability in Bitcoin and in the other systems that use the same recipe and are immutable is one of the most important features. It is the feature that provides for transparency and trust, that removes counterparty risk, that makes the system neutral towards transactions, and that provides censorship resistance. And if you take that away, then what you're left with isn't as useful. Part of the logic here is the idea that maybe transactions should be reversible so that consumers can get refund. But that's a fundamental misunderstanding of what a transaction is. A transaction is a system that guarantees that the program, the script inside the transaction will be executed exactly. And if it's just a straightforward payment, yes, that will be an irreversible payment. But if the script says, pay Bob for a cup of coffee, unless there is a dispute by this third key escrow, or a refund is requested within 30 days, then that script, which is much more flexible, that gives you a lot of very interesting options for consumer protection, that script will be immutable. That script will be executed exactly as predicted. And that's a really powerful feature. So immutability doesn't remove consumer protection. Immutability allows you to have programmable consumer protection determined by the person who's making the payment, and then guarantee that it will execute exactly like that and no one can override it. That is a very powerful feature, and removing that from blockchains doesn't make much sense to me, at least. Olani asks, does the original developer, or do the developers of Bitcoin software have some level of control over the official release of this software? Yes. In fact, there is a team. And you can watch this. I think it's interesting to go and look at it. If you go to github.com/Bitcoin/Bitcoin, you will find the Bitcoin software. And you will be able to watch. There's at least 80 very active developers. That's 80 very active developers, as well as probably another 150 developers who have made small contributions here and there. And the software is developed in a very public way, with all of the contributions, discussions, bugs, requests, etc., managed in a public way. There is a release manager. The release manager is a person who simply coordinates the scheduling and packages up the changes that other people make in order to have specific versions So they assign a version. They're like a librarian, really. They handle the process. They're not in charge. They don't make decisions about what gets added and what doesn't get added, other than when things get added. And all of the decisions are made through a process of community consensus and collaboration. And you can watch that happen in real time. So the developers of Bitcoin software collaborate. None of them have really ultimate control. They can all be overridden by others, and they have to arrive at some consensus. And there are official releases. If Bitcoin technology development is supposed to be open source, asks Olani, could there be a situation where there would be future Bitcoins, several different forks, like Bitcoin 1, Bitcoin 2, Bitcoin 3? Yes. It's not a situation in the future. It's a situation in the present. There are multiple implementations of the Bitcoin software, some that are absolutely compatible with what's called Bitcoin Core, which is the primary implementation. Some that are incompatible with Bitcoin Core and competing against Bitcoin Core. And if a majority of the miners, the exchanges, the wallets, the merchant services, and the users decided to switch to a different version, they could actually modify the blockchain in what would be really a hard fork and make it incompatible. So everybody gets to choose what software they run, and through that choice, consensus emerges on the network. There is plenty of competition within Bitcoin, both at the software development level and in terms of choosing what software each participant runs. Holani also asks, so far, Bitcoin is the highest capitalized digital currency in the world. What factors could have been responsible for this? Well, I mean, the really one factor is the main factor. The main factor is that Bitcoin was first. Bitcoin was first, and it was good enough. And it continued to grow. And all of the systems that are designed based on the same ideas that differentiate have not been able to differentiate enough, capture enough market share, compete well enough to have greater capitalization than Bitcoin. And of course, Bitcoin continues to change and evolve and develop. And so that's why it's currently the highest capitalized digital currency. The market has invested more in Bitcoin than any other system. Let's see a couple follow-up questions, and then we're going to start wrapping things up. Hello, Andreas. As someone not savvy in hardware, I have a tinfoil hat question. We can trust open source software, but why should we trust hardware wallets? How to be sure they are secure? This is a really, really great question. And it's not a tinfoil hat question. You should not blindly trust hardware wallets. You should only trust hardware wallets that have undergone significant peer review, and you should only trust them if you understand how they work to a certain extent. So first of all, most of the successful hardware wallets use firmware, which is the programming of that hardware, that is open source. So we can also examine what's running on the hardware. The hardware can be investigated. You can open up the case of a Trezor wallet and look and see what chips it has inside. A lot of these are very standardized consumer-level chips that are broadly available. We know how they work. And they run specific firmware, which is open source. And you can validate. You can install the firmware yourself. You can compile it and install it, and then you can test the device and make sure it does what it does. Hardware experts have tested these devices. In fact, they've even found some small bugs that have been fixed over time, primarily in the interaction of software and hardware. And through experience, these hardware wallets are now maybe 4 years old. And over these 4 years, thousands and thousands and thousands of people using them to store significant amounts of funds. And we have not seen any problems with hardware wallets being compromised. The real question here is a question of practicality, which is, what do you trust more? The hardware wallet that has been reviewed by security experts and hardware experts and software experts and used by a lot of people, that you can use to apply the same level of security? Or what's the alternative? The alternative is a software wallet, maybe on your laptop. Well, that's automatically less trustworthy. So we know those things are not as secure. What about a solution that you create or write yourself? Again, I wouldn't trust something I wrote myself, because in cryptography we have a rule, and that rule is you don't try to reinvent the wheel. DIY cryptography is highly discouraged. And the reason it's highly discouraged is because it's hard to do. And systems that are heavily scrutinized and peer-reviewed and standardized are much better than trying to build your own. So you trust hardware wallets because they've proven their security, and they are continuously under scrutiny, and because the alternative is to trust systems that are clearly less secure and much more frequently hacked. Let's see what else. Wim asks, I understand every miner can choose which transactions from the mempool to include in their candidate block. So different candidate blocks can contain different transactions, right? Yes. If miners are acting independently, it is in fact likely that every candidate block will be different. 99% of the transactions out of, say, 1,000 transactions, maybe 990 transactions are the same. But there will be 5 or 10 transactions that are different. And there will almost certainly be differences in the order in which the transactions are included, based on either different selection algorithms for choosing which transactions to include, slightly different variations in the version of the software of Bitcoin they're running, as well as differences in timing as to which transactions they see in which specific order. So if you have 2 transactions that arrived and look almost the same value, and they arrive more or less at the same time, well, different miners will see them arriving in a different order, and they'll include them in their block in a different order. So you'll have all of these subtle variations. And what that means is that effectively, the chances of having an identical candidate block are not very good. Even the clock time in the block, of course, is going to be slightly different by a few milliseconds or seconds. And so candidate blocks are all different. They're all unique. Every miner is working on a unique candidate block that has 99% or 95% overlap in terms of which transactions it contains with other blocks, but the ordering and many other details will be different, except for one set of circumstances. Miners who operate out of a pool, depending on the policies of the pool, some pools do all of the transaction selection themselves. Most pools do that, in fact. And one of the reasons that miners use pools is so that they don't have to maintain a mempool, and they don't have to maintain transaction validation. They outsource that essentially to the pool, which makes the pool quite powerful in that way. And in that case, the pool decides what goes into a candidate block, not the individual miners. Some systems are hybrid. The pool has a candidate block, but the miners can make adjustments, adding or removing transactions from the ones recommended by the pool. So there's all kinds of variation in the system. If miners are mining for a pool, most of the time they're going to be working on an identical candidate block. If they're mining solo, almost guaranteed they're going to be working on an entirely different block, which has 95% overlap in transactions, but a different fingerprint because of subtle differences. All right. And that is the last question we had from the audience. Thank you so much. The timing was pretty much perfect on this one. This was session 3 of the massively open online course in digital currencies for the University of Nicosia. Today, we discussed the basis of cryptocurrency, cryptography, digital signatures and hashes, and the history of mining. Great questions from the audience. Really, really great questions today, both from the forums and the live audience. Please remember, ask questions on the forums, engage in conversation and collaboration with your fellow students so that you can find the answers yourselves and explore the topic in more depth, but also to help us prepare by giving us lots of great questions in advance for our next session. This is Andreas Antonopoulos, and I'll see you next week.